Good day, and welcome to the Plant Engineering webcast, Move the Manufacturing Enterprise to the Cloud, brought to you by CFE Media and Technology and sponsored by Epicor. I'm Kevin Parker, an editor with CFE Media. We're joined today by Greg Marsh of Aptiv Corporation. Here are some tips to help you get the most from today's webcast. If you experience issues with the slides or audio, refresh the browser or click the Refresh Media button under the presenter's picture. Control the volume of this webcast by adjusting the volume on your computer or on the webcast platform. For technical problems with the audio or slides, click on the question mark at the top right-hand corner of the screen to access a list of system checks to try before contacting an online technician. If you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. The Ask a Question box is also used to ask the speaker questions. The live Q&A session will begin after the presentations conclude. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. We'd now like to share with you a brief video from today's webcast sponsor, enterprise software provider Epicor.
Manufacturers are facing a barrage of information about how new disruptive technologies will change the face of their industry. But for manufacturers to embrace mobile, social, analytics, cloud, and Industry 4.0, they must have a clear understanding of the technology value add within the context of today's business environment. With all this talk about Industry 4.0 and data deluge from all the interconnected devices on the factory floor and analysis in the back office, manufacturers may wonder, where does ERP fit into this new digital frontier? The reality is that ERP is more relevant in this equation than ever before, and manufacturers need the ability to contextualize data and integrate it into downstream process flows. To do this, ERP systems must be reimagined to meet the needs of new and emerging manufacturing technologies. Responsiveness demands simplicity and mobility, with tools designed to meet the specific needs of specific users. With an ERP system that delivers this, manufacturers can check off a big box on their Industry 4.0 readiness checklist and make good on the promise of real-time, actionable intelligence.
Welcome back. Today's main presenter, Greg Marsh, is a solution architect and manufacturing practice lead at Chicago-based Aptiv Corporation. Greg has designed and deployed multiple end-to-end analytics solutions in the manufacturing industries. Moreover, Greg has an electrical engineering degree and experience programming PLCs, integrating manufacturing execution systems, and deploying supervisory control and data acquisition systems. He focused on operations and data science in studying for his MBA from Georgetown University. During his presentation, Greg will outline the workflows and architectures relevant to using cloud computing in the manufacturing enterprise. But before turning to Greg's presentation, I'd first like to share some background on markets for cloud-based systems. As you can see, most companies see cloud as an infrastructure topic, looking from the executive management point of view downward. McKinsey Digital recommends the following: that cloud should be part of an overall strategy discussion. In other words, is it empowering the business processes that it is automating to make them more flexible and more conducive to delivering results? They also recommend that you incorporate cloud into risk and compliance discussions. And it may very well be that the cloud computing providers have greater insight into security than any given enterprise does because of the economies of scale it's able to bring to the problem. They also recommend that you develop cloud capabilities throughout the organization. And it's really important that it become a question of human resources and talent retention, simply because as I think all of us are aware to a greater or lesser degree, we're being squeezed by a severe skilled labor shortage within the manufacturing industries. So if one company is capable of providing web services to a dozen manufacturers, that's much easier or more economical than each of those companies trying to provide those services itself. And then finally, the financial impact of cloud is especially important because you're shifting from capital expenditure spending to operating expenditure model. And next, I'd just like to talk a little bit about exactly what the levels of cloud computing spending are. And in fact, it was noted today that in the first quarter of 2021, spending on cloud services exceeded $40 billion for the first year. In fact, it almost attained $42 billion, and it's been growing. It grew within the last year on a 35% year-over-year basis, according to the analyst firm Canalys. Amazon Web Services led the way with 32% of the market. Microsoft Azure with 19% came second, and probably has a stronger stance in the manufacturing industries than would otherwise be the case because of its historic position in the industry. And then Google Cloud with 7%. So AWS contributed more than $4 billion to Amazon's operating income in the quarter, and Microsoft Azure revenues grew by 50%, based primarily on their hybrid cloud approach. Here you can see a number of definitions and terms that are relevant to cloud computing. Cloud computing itself, the corollary to cloud computer, which is edge computing, where we put computing resources at the process and split tasks between the cloud where latency is unimportant and the more time-sensitive computing is done at the edge. Many of you know about supervisory control and data acquisition, which is kind of the workhorse industrial control system in plants today, and first introduced in the 1990s and growing to be billion-dollar markets in the years immediately thereafter. Manufacturing execution systems were also introduced in the 1990s. Those are very industry-specific systems used for scheduling and work documentation on plant floors. And finally, ERP, or enterprise resources planning, which tends to be the single source of truth in most manufacturing companies and combine the very most important processes such as HR, manufacturing, distribution, and finance. But in the last 20 years has really expanded its footprint to almost every corner of the manufacturing enterprise. Here are some results from a survey that Plant Engineering did just as the pandemic was getting underway about almost a year ago. And as you can see, our respondents are very familiar with the concept of cloud, both for transactional systems like enterprise asset maintenance, but also on the plant floor for optimization of process control and automation. And you can see the results are really quite in line with some of the statistics mentioned earlier, because Canalys concluded that despite all of the progress and tremendous growth in cloud computing over the last year, most enterprise workloads have not yet translated to cloud. So there's a lot of room there for continuing growth of this segment of the computing markets. Here's some more survey results looking at cloud computing for enterprise systems and also in condition-based monitoring. If you look at the case studies that we are seeing for use of cloud alongside of analytics By far, the number one application space is condition-based monitoring and machine-to-machine connectivity. And you can see that reflected here, as well as indications that our engineering audience feels they are more forward-looking when it comes to the use of these technologies than are their executive ranks. Of course, one of the biggest issues when it comes to this developing market is distrust regarding data, and that encompasses not only your basic block and tackling of protecting your assets from cyber attack, but also who you're willing to share that data with. When you get into an atmosphere where on the plant floor you have the owner operator, you have the equipment supplier, you have in-house resources, and you also have software providers or other third parties coming in and wanting to look at that data, it brings up some important issues pretty quickly. So that's some discussions related to that are ongoing, to say the least. Here, based on the survey results, are some important issues that are related to cloud. Number one, again, we mentioned the economies of scale that cloud provides and the ability to get to resources that are very scarce today. You're investing in the future, and it takes away having that enterprise provider gives you a lot of other benefits as well. You don't have to watch your own system to make sure you're current on regulations or on versions. And you're able to customize your platform, hopefully to even a greater degree than otherwise. And subscription pricing is certainly a differentiator. Here are some other good questions to ask if you're in the market for cloud services. Can the solution be customized? Is it scalable? What is the track record of the provider? Is it a hosted or true cloud solution, whatever that may mean? And then obviously SLA commitments and transparency. And then finally, I'd like to talk about a recent study from Interact Analysis that was devoted to rotating equipment as an area of focus, which I think is of very clear interest to readers of plant engineering. And the report shows that predictive maintenance was close to 120 million in 2019. It's based on continued progress in smart sensors, and SaaS as a form of cloud computing is liable to be the most important parameter. So we're now ready to turn to Greg's more plant floor oriented supervisory control and MES presentation. And without further ado, Greg, I'd like to hand it over to you.
Great. Thanks, Kevin. Appreciate the intro. So actually, I'm going to tick back here and talk a little bit about myself. I know Kevin mentioned my background, but I started off as a controls automation engineer, an electrical engineer. So I spent the first 5 years of my career programming PLCs and designing electrical cabinets and doing startups on plant floors. And from there, I kind of decided to get more on the business side. I was very much interested in data science and analytics. And so I went to Georgetown, got my MBA, and I landed at Aptiv here in Chicago. And just a quick plug for them, just 3 things about us that I love. We're tech agnostic, which means, Kevin mentioned all the 3 different public clouds and all the different tech out there. That's something we pride ourselves on. We are small teams oriented, and we're also really focused on getting business results. And I think that's just important to mention, just because you might see that kind of influence my presentation a little bit, because I have some opinions and I think we match well with doing these kinds of projects. But ultimately, so today we're talking about moving the manufacturing enterprise to the cloud. And what I want to do is start off with why this is happening, give you a little bit of the history, followed by just a walkthrough of what a smart plant in the cloud might look like. And then finally, just a discussion on how you might get started doing this for your own enterprise if this is something that's interesting. And so to start, let's just talk about the history of the Industrial Revolution. I think IR1 is, you're probably all very familiar with. That's when we went from using our hands and animals to using actual machines. And so we started using steam and water-powered engines. And then IR2 came along in the early 1900s, and that really is characterized by making the original Industrial Revolution more efficient. So we added electricity and steel and railroads. Next, here in the mid-20th century, we hit the digital revolution. And this was really a paradigm shift in how we do our manufacturing, right? We're no longer, it's not just about machines, it's also about using computers. And what's near and dear to my heart as a control automation engineer is adding all this automation so it's not so human driven. And so from my perspective, just like how IR2 made IR1 more efficient, what Industrial Revolution 4.0 is about making this initial digital revolution a lot more effective and bringing in a lot more efficiencies from that. And so today I'm just going to talk about what that means and what that might look like for one of your plants or facilities. So really, in my opinion, IR4 is about leveraging and expanding our plant's operational technology that we implemented during the last 50 years, 60 years, and adapting it to all these new available services that have been created across all the different industries. So first and foremost, I'm just going to discuss kind of the three big work streams that come out of IR4. The first is advanced analytics, and Kevin already mentioned it, but the biggest buzz is around predictive maintenance. Some other people call it like predictive quality. It's just this ability to create a digital thread of your production lines, identify patterns off of live and historic data, and then like sending alerts in real time, and just having models that are constantly adapting to your processes as they improve. And so if you ever hear of you doing AI or machine learning or something like that, this is where I think advanced analytics can help you out. Next is just new hardware. And the thing I want to just mention explicitly, because it will come up later in the conversation, is smart sensors, IoT. And these are devices that connect directly to the internet. And in a consumer sense, you see these as like Wi-Fi thermostats or, you know, digital locks that you can control with your phone. But in an industrial sense, these have become kind of big peripheries and on our plant floors, and then being able to use this data to improve our processes could be really valuable. And then last is just smarter processes and using our data to build our processes. So specifically building out a more sophisticated MES or getting to near real-time reporting. So specifically on the MES, it's about capturing accurate information on your labor, on your scrap, on your downtime, on your tooling, incorporating paperless workflows into your activities, and just all around making your manufacturing processes a lot more traceable, and even building these processes as like avatars and applications to the end user. But just a quick caveat, you know, again, I started as an engineer, and I think there's a huge opportunity to leverage all these cloud tools out there. And I'm going to kind of show you an example of that right now. But I do not see this replacing operational technology, the actual OT, anytime soon. So, and it really comes down to latency and just the tech not quite being there. And maybe this is one of the reasons the manufacturing industry has lagged behind in terms of adopting some of these cloud technologies. But the good news is I think we can kind of have our cake and eat it too with the way things can be structured. And so to that, I'm going to just get into one sample architecture just to kind of put a conversation together. And what I want to mention here is there are many ways to do this. Like I'm going to kind of step through these different semantic layers just as an example, just to kind of give us context. And I'm specifically using the Microsoft ecosystem just because that seems really popular in the Midwest and with the other manufacturers that I've worked with. But there's also AWS is actually the biggest public cloud on the market. Google Cloud Platform has been really popular. Building out private clouds like on a rack space is also a perfectly reasonable thing to do. And each one of these services that I mention are replaceable by like hundreds of competitors out there. And so if you find yourself getting pinged a lot by different IoT providers or, analytic providers, that's because the market is really fractured right now. There's a lot of people trying to do this stuff. And I think that's really good for us as consumers because gives us lots of opportunity and it helps us control costs and just allows us to do lots of different kind of pilots and POCs. So to that end, let's just kind of break this into three pieces. And the first is around collecting our SCADA and IIoT, our industrial IoT, into the cloud. And not to bury the lead here, the goal is to combine this OT, our operational technology, and our information technology together in real time. And so the first step is obviously to get our OT up into the cloud. And so what does that look like? In my experience, kind of the current use case is we have hardwired all of our I/O in a panel out to our various devices. Then we program our PLC to control the hardware via feedback loops, via all our fun wrong logic or however you do it. And then we collect that sensor data. And from what I've seen, most of that sensor data is used to show compliance and maybe to do a little bit of kind of reactive analysis of what equipment is doing. But mostly the focus is on that operational technology and what's going on inside the plant. For the cloud use case, what we're looking for is both a combination of using hardware that already connects to the internet. So these IoT devices that might connect to the internet either directly or via edge devices, which are simply devices that kind of bridge the gap between things that can communicate to the internet and things and the cloud itself. Or, and then also pushing all this supervisory control data from all our sensors into a data lake. And this is kind of a buzzwordy term, but the idea here is that data lakes are where we can just drop or where as we collect data, we don't do anything to it yet. We're just collecting it and loading it into a central spot that's accessible in the cloud. And so this is just very different from putting it, say, on a historian SQL Server database that maybe you've kind of set up to sample your sensors every 5 seconds or something like that. And those samples are then plugged into a table on-prem. And that data is nice and protected in your plant subnet, but it's totally inaccessible by some of these really cool cloud applications that we're about to get into. So just a couple things I wanted to mention about this. Hardware is really coming along with this. Like a lot of it comes with Ethernet, 4G, 5G kind of transmitters, almost standard. And this is to allow us to connect our information directly to the internet. But again, just to kind of bring it back to what I mentioned earlier, I don't see these as controlled devices necessarily. Like, I don't see the cloud as a replacement for a PLC anytime soon. And it really comes down, for me, it's latency. I also worked a lot in like pharmaceutical and dairy plants. So there's a lot of stainless and we had to deal with all kinds of like my cell phone didn't work in a stainless plant. Obviously, there's ways to get around that, but just some considerations on the hardware side as to setting up these devices on your plant floor. But ultimately, again, the goal is to get us into the data lake so that it is more analyzable by people that outside of the plant, specifically people like data scientists that might be inclined to do more kind of deductive analyses like these predictive maintenance models or identifying process bottlenecks, things that just are not really viable for plant floor engineers, or is not really the priority for people in that role. One example I just wanted to bring up is I remember spending just a ton of time with a maintenance manager, and what happened is somewhere in the process, we were getting consistently bad batches. It was a yogurt plant. They weren't bad batches. They would just take a lot longer than expected. And we could not figure out what was going on just from a HMI perspective. Looking at the HMI, looking at the code, everything looked fine. And ultimately what happened is, like, when we were injecting the yeast into the milk before the fermentation process, the valve was kind of chattering and only letting in as a lot less. And there was an issue with the flow meter, and it was letting a lot less of this product into the milk. And that caused all kinds of problems downstream of that process. And I just wonder, and we were doing things like swapping out hardware all day, trying to figure out what to do. And I just wonder if we had access to, the state of the valve or all the variety of signals and sensors available in a different format, like what I'm talking about here in a data lake, if we would not have been able to discover that issue more digitally rather than kind of a guess and check approach. So next, the second piece I wanted to talk about here is integrating it with your ERP, with your other source systems. So for me, the cloud, this kind of analytics solution is not a replacement for an ERP or a planning tool or a procurement application. It's a place for us to kind of integrate all this data together. So this to me is really the guts of a manufacturing enterprise and the cloud kind of analytics project. So the current state of things is we can hook up our HMI and maybe some reporting applications to our PLC and or Historian DB all within the plant. And we can create a lot of what I would say kind of reactive, simple reporting. What has already happened? So trending of our sensors and things like that. But what we want to do with the cloud is not only ingest all this rich OT data, but also combine it or also ingest from our ERP, from our lab, from our procurement, from our FP&A apps, from our other facilities, who knows, and then structure the data that makes it accessible to your downstream kind of IT resources, your report developers, your data scientists. And so we can kind of shift the question from what has already happened to, okay, more, how can we improve this process? So more deductive kind of analyses. So the one thing I want to emphasize here is creating the data lake is not enough. Just dumping data, relatively semi-structured or unstructured, from all these devices or from these other sources into a big, essentially, file share, if you want to think of a data lake like that, is not enough. There needs to be a step where we model the data for the business to actually leverage, to actually make it accessible. And that's what that kind of final step, I have an arrow drawn from a discovery layer into a data warehouse. And that's where we're actually spending some time as data engineers, as opposed to plant engineers, to organize the data in a way that, again, is reportable, that we can actually turn into an operational report. And I liken it to, having a bin full of bolts. Like, you can just dump all the different kinds of bolts into a big bin, and then when you need one, you can take a big handful and pick through and the ones you want, in which case you're taking the time at the point of read, at the point of when you're getting the data to figure it out. Or you can spend some time when you're actually dumping it in there to organize it out, and that just makes the reading and usability of the data that much more. So just like you would do for your hardware, getting it organized, you do the same thing for your data. Ultimately, what happens is a hybrid approach. You are collecting all kinds of inputs. You're collecting all this data. It's landing in the lake. And then on the other side, you're identifying the analyses you want to do. You're discovering these business use cases. And you start to model the data that's relevant to the reports and the use cases that you're actually trying to build. So what my suggestion is to kind of avoid doing data engineering work in a vacuum. Actually do model out your data if it makes sense for an analysis you're actually trying to do, and not before. So just kind of straddling that line between structured and unstructured. But then, so finally we have our data nice and organized. What are we going to actually do with it, right? So here's the most interesting part about this IR 4.0 is all of these services that we can leverage. They've already been generated by other industries, and so they're available, and so let's just kind of take this step by step. The top one I've already mentioned is advanced analytics. I think this is synonymous with a lot of other terms. So you consider artificial intelligence, you consider machine learning. Let me just give you a solid example of what a machine learning case might be for manufacturing. I want you to consider some sort of metric or variable that you're trying to optimize. So like a placement of a label, or a flow through a meter or something like that. What data science lets you do once you've kind of structured your data is say, okay, I want to minimize this error, I want to maximize this output, whatever it is. And then also, here's thousands of inputs that may or may not affect this output. And computers will automatically, and computers are able to actually dig in and discover which of these inputs are the levers that actually affect the output the most. So you're no longer kind of like a lot of times I feel like you have a gut feeling for what might be affecting your processes, how you can optimize these different outputs. But when computers are able to just see these things that humans cannot see. And also when you're kind of trying to pitch that plan up the ladder to the management, to the plant manager, it is so much more effective if you come to them with a data analysis, with a data model to say, look, this is what the data is telling us. I think this is where we have a bottleneck. This is where we can optimize. It makes sense in the data. So it's worth the investment. You can actually calculate that ROI because you've done the work on the data side. You've kind of modeled it digitally before you attempted to do it physically. Now, what I described is called a principal component analysis. Is really powerful, identifying all the inputs that have the most effect on an output. There are also just hundreds of other machine learning type analyses out there. And these AI tools out there are incredible. And maybe as kind of plant engineers, we're not the ones that are doing these AI kind of models. But I would say, just as an electrical, anybody with an E degree or any sort of engineering degree would be very capable with kind of minimal coding. You don't have to know R or Python anymore. It used to be you really had to kind of be into these statistical languages before you could put together some of these optimization models. And that's just not the case anymore. Tools like Azure ML have really abstracted that away. So as long as you have the data available, you can do a lot of really cool work. So next is around the MES, the Manufacturing Efficiency Execution System. And so again, we've captured all of our activity in our plant, and now we want to be more proactive. And for me, an MES kind of bridges the gap between the ERP that's done all the planning and forecasting maybe and all that stuff, and then your actual OT, what's actually occurring. And the example of the MES, one of the MESs I implemented was pretty straightforward. It was a dairy plant, so we had to clean the lines, three times a day or whatever it was. And we had all these temperature elements and flow elements and conductivity elements. And we were collecting all of this sensor data just with samples every 1 second or 5 seconds like that. And it was really hard to kind of pull out, okay, we ran this clean from here to here, and here's what the sensors read, and just reporting that out, or even viewing that occurring in near real time. And obviously you could see that in the HMI, but anybody outside of the control room, it was really hard to observe what was going on in terms of quality of the plant floor. And so we developed an application there because the data was available. We were able to, build a lot richer reporting environment, one that allows us to click around, select specific cleanings, and chart that out without having kind of the pain of having to write out, actual queries or something like that. And there's again, I'm kind of talking about a custom MES. There are a bunch of actually pre-canned, pre-built MESs that you probably already have. But even when you're integrating these kind of pre-built MES, they still need the data available. And that's, again, one thing that is really nice about having this OT and IT data in the cloud and already kind of pre-integrated, is it creates this really just rich data source for these existing services and tools to use without you having to kind of reinvent the wheel. One other thing I wanted to mention is what's nice about the cloud is your ERP lives over here on the business side, and all your operations, plant operation lives in your plant, and those are sometimes just hard to interconnect. Like I said, if you have your MES only pointed at your operations data without any sort of connection, it's hard to kind of close that feedback loop outside of maybe like Excel extracts or something like that. So this just, again, building a model in the cloud makes the data so much more accessible to all these different tools that would be interested in the plant's performance and all of this operational data. So this for me is what IR 4.0 is about. It's about putting our plant into a position to use all these awesome cloud technologies that are already used by other industries, and to make all these processes that much more efficient for us. So just to kind of wrap things up, I wanted to give you you know what? I'm missing a slide. So, I see. It got ticked after. So, how to get started? What does a project look like this? And this is why I kind of mentioned all of Aptitive's quirks about being small teams and being agile when it comes to these projects, because I'm laying out just a couple kind of phases that are 3 or 4 months for a couple people to start to realize your manufacturing operational data in the cloud. And ultimately, kind of big picture, my big recommendation is to start from the end. I've been talking so much about ingesting data and integrating it together, but where I really think you should start is on the business side, is identifying a use case that will actually create some ROI for your operation. So take a step back. What can we optimize? What, again, like what I mentioned before with ML, what variable can we actually, if we optimized, if we changed, would actually have a significant effect on our operation? Or where are our pain points, right? That's the classic, like, consulting question. Where's your pain, right? It's, and I obviously there's a lot of truth to that, though, understanding or kind of identifying where we can get the most ROI from this kind of investment. So step one, identify 100 use cases if you can. Then try to prioritize them, put them in order of what you think would be the largest ROI for the company. Step two, actually make sure you have the inputs you need to make that happen. So just as an example, if you're just trying to reduce waste, but you don't, out of a certain line or something like that, and you don't track the waste out of that pipe, well, that's a problem, right? Because these machines are trying to optimize numbers. They're not, so we're talking about, and maybe it doesn't make sense to install new hardware or new IoT gadgets to track that physical waste. And so in that case, I have two recommendations. Either one, pivot and do something else. I think that's okay. Or number two, find kind of a proxy for that. So maybe, hey, we don't know the flow through this drainage pipe. Maybe we use a sewage bill or something like that. We try to optimize on that basis. And the reason I bring it up is I feel like a lot of the times with these projects, they just say, I want to do AI, right? Let's do some AI. But that's not how you get started on a project like this. You actually have to identify a KPI that you're trying to optimize, and then also make sure you're actually collecting the data that makes sense as inputs that would be highly correlated, in other words, to that output. So the third step, engineer some sort of semantic layer. So do spend some time and kind of model something out. And it really comes down to don't try to work directly with this raw data, because even if you get it to work on this model, you lose all the ability to reuse it for future analyses. And so I think building that kind of centralized semantic layer, whether it be a physical database or it be kind of a virtual view of the plant, it doesn't matter, but do invest some time into actually building a foundation of pulling that data end to end and creating a modeled view of that data that is analyzable and accessible. And then the fourth thing seems really obvious, but actually do plan on delivering something. have some final dashboard or report or scored machine learning model that you want to put into production that will actually demonstrate that ROI. And it's all about, I think, as engineers, again, it's about mushing our OT and our IT together and getting business and the plant engineers all to collaborate. And that goes a long way to be talking in terms of ROI and those specific processes. So just to conclude with IR 4.0, after kind of the first phase, so I talked about kind of a phase 0 strategy project, a phase 1 foundational solve a problem. Then you go on to phase 2, and that's another problem. And you build on top of that existing modeled data, and you continuously build this. These kinds of analytic cloud projects, they never end. You're always trying to find the next efficiency, the next thing you can do to improve your processes. And the ultimate goal really is to allow these downstream models that you build to have influence over your plant operations and other enterprise applications. In other words, the dream is to kind of close the loop, all these ML models and machine efficiency things to come back and allow the machines to control other machines with kind of minimal human intervention. Obviously, like I said at the beginning, we're a ways away from that, but that is the dream, to kind of create this all-encompassing loop between our operations, our plant operations, and all of our other enterprise IT data. So I hope you found that interesting. Kevin, I guess I'll... if you're
thanks so much, Greg.
Please email me, connect with me on LinkedIn. There's my website as well. Otherwise, I'll pass it back to you, Kevin, for questioning.
All right. Well, thanks so much, Greg. It was really interesting, and it's really a fascinating environment that you're working in, where on the one hand, you mentioned ladder logic as being a programming language for PLCs, and on the other extent, you were talking about Python as a programming language for AI. How are plant floors reacting to that? I mean, do you still find a lot of ladder logic in manufacturing plants, or is that being replaced by the guys who do real software development in BASIC or otherwise?
Yeah, I mean, I think from what I've seen, PLCs are still very much programmed in with that kind of ladder. Like, I mean, at the end of the day, we're dealing with hardware, and it's either on or off, right? And you can program that with a lot of different languages. But so rung logic works for hardware languages. There's a lot of other hardware languages out there, like you mentioned. But I guess my point is, the statistical languages, the languages used for these AIs are definitely different, but they're getting abstracted away. So if what you know is C, for example, or something like that, that's fine. Because if you look at these kind of ML tools, if you have a well-designed engineering, it's a lot of kind of dragging and dropping modules for you guys that work with like MATLAB and things like that. It actually might feel a lot like that. Of course, MATLAB is RNS and stuff like that.
Sure. Great. Thank you. To our listeners, type your questions for Greg in the Ask a Question box. We'll get to as many as time allows. And remember to download a certificate of completion and a copy of the presentation using the Event Resources tab on the left side of the screen. One question that it's just maybe sound incredibly naive, Greg, but what is the difference between a data architecture and a data model? Because they seem to throw around that data architecture term so loosely that it tends to lose meaning, if you will.
Yeah. Well, I'd say in the context of this presentation, what I meant by architecture is this whole kind of end-to-end solution. So how do we pull data from our plant floor into the cloud, then transform it into a warehouse, then pull it into our ML application? Like, there's a framework to moving this data around. And like I mentioned, I have us kind of centralizing in a data warehouse. There's lots of other architectures out there. Like, you could put data virtualization on top. You can ingest using lots of different tools. So to me, those are our architecture questions. The data model then is a matter of asking kind of the business question. It's the matter of kind of designing your data in a way to answer business questions. So the way I think of it is kind of building tables based on the way our plant operates, or the way our business operates, and kind of building transactional tables that represent all of those different workflows, and creating a model of data that reflects what we're trying to achieve as a business, so that it becomes more accessible and easily understandable. And so I guess hopefully that makes sense. The model is about how the data is structured, whereas the architecture is more the larger solution.
Right. The architecture is kind of the vocabulary that you have, and then the models would be asking more specific questions, perhaps.
Yeah.
So when you look at these data architectures and data models, are there specific areas where the integrations are more difficult than others? In other words, when I'm thinking about time series data, the operational side of it, is that significantly different than trying to integrate with ERP transactional type systems?
Yeah, I mean, just to kind of start off, one great thing about the cloud is we no longer have to worry about storage. I know that sounds weird, but storage is so cheap on the cloud that we can go ahead and kind of treat everything almost as transactional. Like I have most of our architecture is kind of insert only, in the sense that even for our ERP, if I were to update a column, I would rather just take that update as a new row, insert it up into the cloud, and just flag it as the current version of the row, for example. And so worrying about all those create, update, delete kind of statements becomes kind of it becomes a non-factor, because storage is so cheap, and because compute has become so powerful that it no longer needs to worry about analyzing the volume of data involved. And that's kind of what the big data revolution has done for us. And so that's where IoT, which is just time series by its nature, or all the SCADA data is sampled data from all these sensors, that's really usable here with the new technologies. That's kind of what these technologies have been built for.
And the efficiency there in many cases with the IoT data, for example, is by not streaming it through your SCADA system, you're not putting a heavier load on that system, and you're finding a much less expensive way to share that data with operations and without it.
Yeah, well, and you might intentionally keep those two kind of IoT devices connected directly to the internet, and your SCADA data, you might intentionally keep those separate just for security reasons too. Like you don't want to give access to your plant devices even into that subnet. And so it makes it all analyzable. You can pull your SCADA into the cloud, you can pull your IoT into the cloud, you can pull your ERP data into the cloud, mix it all together in an analytics solution in a cloud data warehouse. And there you go, Bob's your uncle, start analyzing away.
And are you willing to buy into the proposition that your cloud service provider might have more knowledge about efficient cybersecurity than you do in-house?
Absolutely. Once things get to the cloud, the concern for me becomes, phishing, and obviously, definitely like the physical security of the data, I think is just as secure in the public clouds as it would be a private cloud. Obviously, you still have all the concerns of, the classic phishing, virus, getting people to open an email and download a virus and all that kind of stuff. But a lot of that, I give AWS much more qualified in terms of securing data that way than I would be in an IT room there in a plant. And then obviously there's the factor of I can trip over an Ethernet cord and shut down my plant's IT, and that doesn't really happen in the public clouds.
Good. So then looking at, continuing to look on the operations side as opposed to the enterprise side, what are some of the standards and protocols that, are most relevant to these kind of implementations on plant floors?
I mean, how these devices talk to the internet, I think it's going to really depend on the hardware itself. Like, obviously, I've seen just a lot of the devices with Ethernet plugs and things like that. Like I said, they can have 4G, 5G kind of transmitters, maybe not 5G yet, but that's kind of the future, right? How they interact then with the edge device, which kind of eventually wraps it up into a secure kind of API request up into the cloud, that's usually managed by that kind of hardware. That's what the edge is for, right? It's we're secure within the plant. We send it to the edge device. It wraps it into its secure protocol to send it to the cloud. Things like Azure, they force you to download specific security gateways into your on-prem kind of devices. So it's extremely hard to kind of intercept that kind of these kind of protocols, and it's very common, right? We're very used to working with HTTPS and those kinds of protocols.
Good. You mentioned in your presentation that what you were showing us was a sample architecture, but that there were many alternatives. Are the alternatives and the sample easily classifiable in a few categories, or is it something that just 1,000 flowers bloom?
Yeah, I mean, what I showed you, right, is ingest your data to the cloud, land it in a data lake, move it to a cloud data warehouse. So there's lots of cloud data warehouses. Azure's is called Synapse. Google is BigQuery. There's Redshift, and then obviously Snowflake is the big player right now in the market. And then I suggested kind of modeling it into a data warehouse to make it more accessible. There's a lot of other ways to do that. You don't have to centralize and model. You can, like I said, there's a big trend called data virtualization. You can organize your data different ways. You don't have to be in kind of a star schema orientation. It could be I don't want to throw out buzzwords like data vault or data mesh, but there's just lots of architectures out there, and it really comes down to your specific use case, what makes the most sense, how important history is, how much data there is, how much disparity there is between all the different data sources that might drive which architecture, which data modeling technique makes the most sense for your enterprise.
Good. We're getting close to the final question for today, Greg, and I appreciate your patience with us. But I guess I'd like to ask, I don't know how much opportunity you have to interact with engineering departments in manufacturing plants on a day-to-day basis, but I would just be interested in your insight into how they're evolving. I mean, when I was in an engineering department in the 80s, ERP was being introduced, PLCs were coming on board, so that's when ladder logic started. And 30 years on with IIoT and analytics, that's probably the biggest revolution we've seen since supervisory control and data acquisition. Do you see the skill sets in those engineering departments evolving quickly?
Yeah, absolutely. I think one of the reasons I'm so involved in the manufacturing industry, I still have a great relationship with the old firm I worked with back when I started my career. And the reason they called me up is there is just this huge appetite to build smart plants, right? To make our processes all the more efficient. Like, we've made these huge investments into automation and now what, right? What's the next step? And I see engineers doing it. Like, when I was an engineer, I was already integrating these MESs and execution systems. And again, a lot of these tools have abstracted away a lot of the coding. So if you have that good engineering mind that just sees things as problems, you're going to love working up in the cloud, because there's just so much opportunity to use these different tools, and you will be successful at it, in my mind.
Well, thanks so much for joining us today, Greg, and giving us an opportunity to tap into your enthusiasm. I'd also like to extend special thanks to our sponsor, Epicor, for sponsoring today's event. Now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it, because we use this information to improve our programs. Finally, on behalf of Plant Engineering and Epicor, I'd like to thank you for attending. This concludes our webcast. Thanks, and we'll see you next time.